In this video, we'll be talking about the types of discontinuities that can appear. This first example has actually two different kinds of discontinuities, and the most appropriate one we're looking for this particular case is what we call the holes. Now again, if you remember from pre-calculus, to graph the identify the holes, you would take that function, you'd go ahead and factor everything that you can factor, and you'd cancel out like terms on top and on bottom. You'll recall that the value that actually cancels out in the denominator causes there to be a hole. So there should be a hole at x equals a positive value of 2. Now, the way that we verify this using calculus, if you recall, is by taking the limit as x approaches 2 of that function f of x and identifying that when I actually evaluate that limit value, this right here is the function I'm playing with. So the limit as x approaches 2 of 1 over x plus 1 actually equals to 1 over 3. So if you were to attempt to graph this function would actually behave exactly the same as this function right here, 1 over x plus 1, which we all know again has a vertical asymptote at x equals negative 1. This right here again is a vertical asymptote. It also has a horizontal asymptote at y equals 0. And this function should behave something along the lines of this, where it comes down this way and it comes down this way. Now, the reason why I've made this dotted lines is because I know at the x value of 2, there's supposed to be an empty space right there. Everything else is now solid, but that location there doesn't actually have a function value. So that right there causes a break in the graph visually and mathematically in such a way that that right there is a discontinuity. In the next function right here, which you'll notice is actually the same one that this is, this function all on its own, unchanged, 1 over x plus 1, simply has a vertical asymptote. So there's no more hole in this function because they are two different functions, and this one comes down like this and over like this. It looks again quite similar to that one. The only difference is that hole right there. Well, that location where there's a vertical asymptote, there obviously is not continuity with this graph. For instance, again, the most reasonable way to try and explain continuity is by if I can put my pen down and trace the graph, if it is continuous, I shouldn't have to pick my pen up. The problem is once I get to here, I now have to pick my pen up to start back up over here. So therefore, I can trace the graph only so far. Where is that location where it causes a discontinuity? Right here at x equals negative 1 is a vertical asymptote discontinuity. So those are two very specific discontinuities, number one a hole and number two a vertical asymptote. The jump function is a very unique function. When looking at the jump function, and this function here is actually what we call the greatest integer function, or the integer function in and of itself. That function will look something along the lines of this. It's going to have an open circle at 0. It's going to be the value of 0 up until you get the value of 1. And then, actually I think it's 0 here, open here. And then you're going to go to 1, and it's going to go over until you hit the value of 2. At the value of 2, you're going to jump up to 2, and you're going to come over here to 3. And so on and so forth. This is going to continue on forever. This is not a very common function to work with, but it is a common function that is seen in mathematics. For this particular step function, we have to identify that there is a jump, meaning you're starting at one location, and you have to jump up to get to the next spot, or jump down. Regardless of how it works, simply the function doesn't just continue on forever. And it's not a very special kind of jump where it's a vertical asymptote. Again, a vertical asymptote is not the same thing as a jump. The jump has a stopping point, and then it has to move and then start again. A stopping point, and then it has to move and then it starts again. This one is technically continuing on forever down, where it's never actually stopping. And then it's going to start coming down from infinity and approach infinity in this direction. So this right here is a jump, and again, every single one of these locations, one right here, there's one right here, there's one right here, where it is jumping from one value to the next. So it has a jump discontinuity at x equals 1, it has one at x equals 2, it has one at x equals 3, and so on and so forth. The last function is the oscillating function. Oscillating functions are very, very unique in terms of the way that they behave. The oscillating function, again, for this case, is not that it's an oscillating function in and of itself, like the simple sine function, which is continuous, going on forever and ever and ever, and never slowing down. The problem with this function is that you can't plug in 0. You'll notice that it's sine of 1 over 0. By not being able to plug in 0, what's actually happening with this oscillating function is it looks something like the sine function when it starts out, but as you get closer and closer, it's still going to go up and down to 1, but it's just going to get bounced back and forth viciously fast as it gets closer and closer to 0. Again, it's going to just keep doing this and this and this and this and this and this, and it's hard to determine exactly what the function is doing. We can't be absolutely certain that there's an actual point there in the center, because this function continues to bounce up and down, approaching -1 and 1 consistently forever as it gets closer and closer to the x value of 0. These are the 4 types of major discontinuities: holes, which you can remove, vertical asymptotes, jumps, and oscillating functions.